Today, we shall apply what we studied during the last lectures, all these linear dependence and independence, bases, spanning sets, and so on. So we will use this knowledge for a specific example for systems of linear equations. It's interesting that so we started from systems of linear equations, right? How to solve them. And then we switched to something which is completely abstract, right? So we started from the very abstract, very general definition of vector space, right? Then we introduced subspace, then we introduced linear dependence and independence, and so on and so on, right? So now we will use all what we have proven, all these introduced concepts to the thing which we started from, right? To systems of linear equations. Okay, so some of the results which we will get today, so will look like a little bit, let's say, abstract. But as you will see, that later we will use these results to extremely practical things. Okay, no, it's working. Okay, definition. The row space of a matrix row space of a matrix is the span of the set of its rows. In other words, the row space of a matrix is all possible combinations, linear combinations of rows of the matrix, right? So this is more or less what the span is. The row rank is the dimension of this space. So, which means that this is the number of linearly independent rows. Okay, so example. If I consider, for example, the following matrix, 1, 2, 2, 4. So row space of A, so it's all possible linear combinations of rows, right? Just some real numbers. Okay, could you tell me, so what is the dimension of the row space, or what is the row rank of a matrix?
Is it 2?
Not really, because have a look. So we need, essentially it's dimension of the space is the numbers of the vectors in the basis, right? But the vectors in the basis, they are supposed to be linearly independent, right? How many linearly independent rows we have?
1.
Exactly, 1, because row 2 is 2 multiplied on row 1, right? So second row definitely linearly dependent on the first row. So I can throw away any of them. For example, let me throw away the second row, right? And I will not decrease the span as a result. Do you agree or not?
That makes sense.
Yes, because have a look. This is what I can do. I can write that 2C2 equals to 1, 2, right? And then I'm getting C1 plus 2C2 multiplied on the row 1, 2, right? But because C1 and C2 are arbitrary, I can just say that, let us say that this is just arbitrary real number and that's it, right? So I can throw away the second row without changing the span, right? Okay, so essentially just remember the standard approach we used before. So you consider the spanning set and then reduce this spanning set, throwing away linearly dependent vectors. Linearly dependent vectors. For example, you found that 3 vectors are linearly dependent, which means that one vector can be expressed through others. So then you can throw away this one vector, right? And it will not change the span, as we have proven before. So this is the standard approach. So if you're asked to find the basis, so essentially all you need to do, just find linearly dependent vectors from the span, throw them away, then check that the remaining vectors are linearly independent or not. If they're still linearly dependent, you again find one vector which can be expressed through linear combination of others, throw it away. As we know, span will not change, right? And so on and so on. So, okay. Now let me formulate a lemma. If two matrices A and B are related by row operation, so A goes to B by swapping two rows, or A transformed to B by multiplying the row by non-zero real number, or let me write here elementary row operation. So B, so what you have done that row J is replaced by row J plus alpha row I, just like that. So 3 elementary row operations. So okay, let me write here that I not equal to J and alpha not equal to 0. Then their row spaces equal. Hence, row equivalent matrices have the same row space and therefore the same row rank. Okay, so first of all, what we can say about the rows after elementary row operation. So each elementary row operation performs just linear combination of rows, right? So if we just exchange rows, right? So swap them. So then spanning set for the row for the row space doesn't change at all, right? So we just change the order of the vectors. If we multiply any vector by non-zero scalar, we are getting linearly linearly dependent. So it's a vector, right? So it's essentially we started from some vector and we just multiplied it by a non-zero scalar. So it's one of the simplest cases of linear combination, right? So here, this is also linear combination with coefficients 1 here, right? So you can say it's 1 multiplied on Rj and alpha multiplied by Ri. So again, linear combination of rows. Okay, because the row of each row of B is a linear combination of the row of A, so we can say that each row of B is an element of a row space of A, right? So as a result, we can say that row space of B is included into the row space of A, right? Okay. It follows just because every row of B is nothing else but linear combination of rows of A, right? But from the other point of view, we know that all these operations are invertible, right? So essentially, we can say that we can go from B to A using the same set, I mean, the same type of elementary row operations, which means that the row space of A is included into the row space of B. So from this, it follows that the only possibility is the row space of A equals to the row space of B. Is it clear or not? Please ask me questions, so if it's not clear. So I told you before that all elementary row operations are invertible, right? So for example, how to invert the swap of two rows? Just perform the swap again, right? So here, if I multiply the row by a non-zero number, I can just consider multiplication of the same row by 1 over this non-zero number, right? And it will be inverse operation. So if I replace the row by a sum of the same row and multiple of another row, so I can just consider the following, right? And it will bring my matrix from matrix B, I will get to matrix A, right? So I got that original linear operation, elementary row operations bring from A to B, right? So because they are linear combinations, so I know that the row space of B will be included into the row space of A, right? So because the spanning set essentially consists of linear combination of vectors from the spanning set of B, from the consists of from linear combinations of spanning set of row space of A. Now, because I have shown that I can get from B to A using the same elementary row operations, right? So I can use the fact which we already derived, but now in the opposite direction, to say that because every row of matrix A can be represented as linear combination of rows of matrix B, so I can say that the row space of A is included into the row space of B as well. So, but if we have mutual inclusion, so it means that they have to be, the only possibility is that they have to be equal, right? These row spaces. Is it clear or not? Any questions?
Yes.
Okay. So now, next lemma. The non-zero rows, the non-zero rows of row echelon form of a matrix make up a linearly independent set. So this is easy to prove if we consider, so we got row echelon form, right? But we can continue to the reduced row echelon form, right? And then we will get something like that. So 1, 0, 0. So another leading one, so next leading one, and so on, right? So it's obvious that if we consider reduced row echelon form, so it's obvious that so the number of non-zero rows will be exactly equal to number of leading ones, right? You cannot get, for example, this row from linear combination of any other rows in the reduced row echelon form, because you cannot get this this thing using zeros which are in front, right? So essentially, from in a reduced row echelon form, it's obvious. But in the previous lemma, we have proven that the row space stays the same under elementary row operations, which means that if I start from the row echelon form, I can use elementary row operations to bring my matrix to the reduced row echelon form. But there, yeah, and the row space will stay the same, right? So then it means that the non-zero rows of the row echelon form of the matrix, or reduced row echelon form of the matrix, if you like, make up a linearly independent set, right? Because they can be expressed through each other. Is it clear or not? Please ask me questions if you have any.
Yeah, I was just wondering, so for reduced row echelon, there can be more than one per row. So even if that happens, it's still linearly independent, correct?
Could you repeat, please? What more than one what?
More than one. So for example, like row 1 can be 1 1 0 0 0, and then row 2 can be
1 0 0. So yeah, are you giving me columns or rows?
So like one row can have two different like one, but then other rows don't have those ones. For example, yeah, like that.
So you see, so and here whatever, let's say 1. So idea is that in the reduced row echelon form, it doesn't matter what I have here, right? So I still can see that in the reduced row echelon form, I will have a leading one, and it will be the only non-zero element in the column, right? In the whole column. Clear?
Yes, so that means that both rows are linearly independent, correct?
Yes, yes, because you cannot, for example, using the rows below the first row, right? You cannot create the first row, right?
Yeah, correct.
Because they all have zeros here, right? In the first column. Okay, it means that first row is linearly independent with respect to the next rows, right? So then you can repeat the same consideration for the remaining rows. For next row cannot be expressed through further rows, right? Exactly, because it will be the only non-zero element will be this leading one, right, in the column, and so on and so on. Okay, so now let me give a definition. So the column space. Okay, we did it with the rows, so now let us do the same with columns. Column space of a matrix is the span of the set of its columns. And consequently, the column rank is the dimension of the column space. Which means the number of linearly independent columns. So exactly the same, just for the column space as what we had for the row space. Okay, why this is interesting? Because, for example, let us consider the following system. x b4. How can we write it? We can write it in the following way: x1 1 2 0 4 plus x2 3 3 1 0 plus x3 7 8 2 4 equals to b1 b2 b3 b4, right? So remember, when we multiply column vector by the scalar, we need to multiply every component of the column vector, right? Every entry. When we add column vectors, we need to correspondingly add corresponding entries, right? And column vectors are equal if the corresponding entries are equal. So if you, for example, multiply it here, 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 and it has to be equal to b1, right, as a result. So it's exactly this. Is it clear or not? That this is equivalent way of writing the matrix, of writing the system of linear equations.
It's clear.
Okay, thank you. So, but then now, what will be the coefficients matrix? It's exactly columns, right? Right? So exactly these columns. So, okay, how to get the basis in the column space?
Reduce it to echelon form?
Yes, so really your book recommends you to do the following. Let us perform operation of transposition, which means let us make all columns to be rows and vice versa. So which means that, okay, first column become the first row. This second column become the second row. And the third column become the third row. So now here we can use elementary row operations to bring this matrix to the row echelon form. And from here we know that how many linearly independent rows we have. Two, right? So it means that what is the dimension of the row space of the matrix A transposed?
Two.
Exactly, 2. So, and because we know that elementary row operations doesn't change the row space, right? So we know that row space of this matrix and row space of this matrix are equal, right? We have proven this before. So now we can just turn these rows back to columns, and we can say that the following 1 2 0 4 and Sorry, 0, -3, 1, -12. So it's a basis for column space of A, right? Is it clear or not? So what I've just done.
Yes, I understand. Can I ask a question?
Go ahead, please.
Is it possible to just row reduce A without transposing it and then like pick out the columns that have leading ones and then that's a basis for the column space?
Yes, it's possible. The only problem is that I haven't proven yet that the row operations do not change a column rank, right?
I see. Okay.
So I will do this just in the next minute, essentially. Okay. Let me give a definition. The transpose of a matrix is the result of interchanging its rows and columns. So that jth column of the matrix A becomes jth row of a matrix A transposed. So operation is called transposition. Okay, so I first just used it, and this is the notation, right? So now I gave a formal definition. Okay, now exactly I formulate the lemma, which relates to the question which was asked a minute ago. So row operations do not change the column rank. So essentially, if A reduces to B, if A reduces to B using elementary row operation, then column rank of B, or in other words, number of linearly independent columns of B, right, equals the column rank of A. Okay, we will understand it in the following way. So let us consider A, which is A11, A12, and so on till A1n, A21, A22, A2n, AM1, AM2, AMN. So M by N matrix, right? Okay. Now, if we consider homogeneous system of linear equations, with the same coefficient matrix, then how can we write it? We can write it in the following way. X1 plus X2 plus and so on, plus Xn on the nth column. And all this is equal to 0, right? Right? So, first of all, this system of homogeneous system of linear equations always has at least one solution, right? So it means that there exists at least one combination, linear combination of columns, which will give you 0, right? Right? So it can be trivial combination, which means all x's are equal to 0. So it always, this trivial combination always exists, right? So, okay, now, from the other point of view, I know that elementary row operations, they do not change the solution set. So it means that solution, this set of coefficients here, will stay the same under elementary row operations, right? So if I will change it to some matrix B, right, using elementary row operation, so then I can write it as exactly the same linear combination. Exactly the same linear oh, sorry. The thing is here supposed to be X. Yeah, exactly the same linear combination. So it means that under elementary row operations, the relation between rows doesn't change, right? So, which means that if my row, sorry, not rows, columns, if my columns were linearly independent, so which means that here the only relation was the trivial one, right? So then here also the only relation will be the trivial one. Or vice versa, if here I could express one column through others using some linear combination, so then here exactly the same relation will stay, right? Is it clear or not?
It's clear.
Okay. Now I can I can tell you the following, that here, instead of transposing the matrix, right, and bringing it to the reduced row echelon form, I can do the following. I can just start from this matrix, right, and bring it to the, for example, a reduced row echelon form, right? And then I know that the columns corresponding to leading ones are linearly independent, right? So and it means that these columns form a basis, right? So let me just show you an example. So if I will start from 1, 2, 1, 3, 6, 3, 1, 3, 1, 6, 16, 6. So I can bring it to the following, the reduced row echelon form. So as a result, you can see from here that all columns can be expressed through the corresponding vectors, corresponding columns corresponding to the leading ones, right? So for example, how you can express 3, 0, 0? It's 3 multiplied by 1, 0, 0, right? Easy. So the last column, this one. So how you can express it? Through columns corresponding to leading ones. Could you tell me? So let me write it. I will leave the space for the coefficients. Okay, how to get these two?
2 and then 4.
2 and then 4 here, right? That's it. Is it clear or not?
Yes, it's clear.
Yes.
Okay, so it means that my column space can be expressed as a span of these and this column for, pay attention, for this matrix, not for the original one, right? Because have a look, you cannot get, for example, the first column using just columns from here, right? Because pay attention, here you have 0, right? 0 row, right? So all columns, they have zeros in this as the third entry. So you cannot get these from here, right? Linear combination of this and that. But what is important? Have a look. Here I said that, okay, my column 2 can be expressed as 3 column 1, right? And here column 4 can be expressed as 2 column 1 plus 4 column 3, right? Is it clear or not what I'm doing?
It's clear.
Okay, but we have proven that relation between columns do not change under elementary row operations, right? It means that if here I had this relation, which is very easy to see, right, in the reduced row echelon form, then have a look. Column 2 here is 3, 6, 3. It's equal to 3 column 1 here, right? Clear or not?
Yes.
And in the same way, column 4 here, 6, 16, 6. Has to be equal to 2 column 1 plus 4 column 3, right? 2 column 1 is 1, 2, 1. Column 3 is 1, 3, 1. So let us check. 2 plus 4, 6. 4 plus 12, 16. 2 plus 4, 6. So you see, this statement that a relation between column does not change, right? So is very useful, because what you can do, you just bring this using the Gauss-Jordan reduction, right? Use Gauss-Jordan reduction to bring your matrix to the reduced row echelon form. From here, immediately you can see that all other columns can be expressed through the some linear combination, like here or like here, through the columns corresponding to leading ones. It means that in your original matrix, this original matrix A, so these columns will form a basis, right? So column space of A is a span of correspondingly, so here I can express it through this column and through this column, columns with leading ones, right? So it means that for original matrix, I can express it through this and that column, right? So 1, 2, 1, and 1, 3, 1. Because all other columns are linearly dependent, for example, like that or like that. Is it clear or not?
I understand.
Okay, now have a look. If I know the reduced row echelon form of a matrix, right? And I know columns corresponding to leading ones in the original matrix, I know how to get all other columns, for example, this and this, right? Just I know through what relations I can get other columns. Is it clear or not? So, for example, I can tell you that let us suppose that you know just this reduced row echelon form, and you know this column and this column. Then immediately you can reconstruct this column and this column using the same relations as we have for the reduced row echelon form. Is it clear or not?
I have a question.
Go ahead, please.
So, would you say that the columns that eventually become the ones that have the leading ones in their respective matrices, like those columns form the basis?
Yes, because you see, we have proven that under elementary row operations, relations between columns do not change. So in a reduced row echelon form, I see that this and this, so the columns corresponding to leading ones, they are linearly independent, right? Is it right or not?
Right.
So, but because relations between columns do not change, right? So it means that in the original matrix, these columns corresponding to, I mean, the same column numbers, right? They will also be linearly independent, right? Or not?
Right.
Relations stay, right? And vice versa. These columns which doesn't have leading ones, right? Which do not correspond to leading ones. We know that in reduced row echelon form, they are linearly dependent on the columns which correspond to leading ones, right? So like here or like here. So, okay, I can say that oops, sorry. Yeah. These and these, they come from the linear dependence of all other columns on the columns corresponding to leading ones, right? So, but then I know that in my original matrix, also these columns, the same columns, right, will be linearly independent, and other columns will be linearly dependent on them. Is it clear or not?
It's clear. Thank you.
Yeah, you see, so it's very powerful statements which we have proven. So now we can use all the oh yeah, let me formulate now the theorem. For any matrix the row rank and column rank are equal. So essentially what I'm saying, the number of linearly independent rows is equal to number of linearly independent columns, right? But proof, so it's trivial from reduced row echelon form. So because you remember we said that rows corresponding to the leading ones or non-zero rows in the row echelon form, right? So are linearly independent, right? We have this lemma. But if you bring it to the reduced row echelon form, essentially it means that number of rows of non-zero rows in reduced row echelon form gives you the row rank, right? But at the same time, number of linearly independent rows or number of non-zero rows is the number of leading ones, right? But as we know already, in the reduced row echelon form, number of leading ones correspond to the number of linearly independent columns, right? Which means that so essentially the number of linearly independent rows or linearly independent columns is equal to the same parameter, which is number of leading ones in the reduced row echelon form. Clear or not? Like here, for example. So I brought this using Gauss-Jordan reduction. I brought it to the reduced row echelon form. Okay, obviously these and these rows are linearly independent, right? But what is the number of non-zero rows in the reduced row echelon form. It's the number of leading ones. And for column space, again, so what will be the columns which would span the column space? It's exactly form the basis for column space. Exactly rows corresponding to leading ones, right? Because relations between columns stays the same under row operations. That's it. Okay, now after this theorem, I can formulate the following definition. The rank of a matrix is its row or column rank. So essentially, now we don't need to distinguish between row rank or column rank, right? So we can just say rank. Clear or not?
Yes.
Any questions? Because this is very important. You will be asked many times in your homework and later, what is the rank of a matrix? And so on, so on. Okay, so you just need, essentially, in order to find the rank of a matrix, bring your system to the row echelon form, and number of non-zero rows will give you a rank, right? Or if you are not lazy, bring your system to the reduced row echelon form, and then number of leading ones will give you a rank. Okay, next theorem. For linear systems, with n unknowns, and with matrix of coefficients A, the statements one, the rank of A is R, and two, the vector space of solutions of the associated homogeneous system has dimension n minus r. So these two statements are equivalent. Okay, proof is relatively easy. So essentially, bring the system of linear equations into reduced row echelon form. So then we know that essentially number of free variables, like here, right? So this is the column corresponding to the free variable, and this is the column corresponding to free variable, right? So number of free variables is number of unknowns minus the number of leading ones. But number of leading ones is exactly rank of A, right? Is this. So correspondingly, but the solution of the associated homogeneous system will be expressed as some free variable multiplied on some column, right? Plus another free variable multiplied on another column, and so on. And what is important, that these columns will be linearly independent, because they will be nothing else but yeah, so these columns will be linearly independent because, for example, here, let us consider this. So how can I write solution of the homogeneous system of linear equations? So essentially, this is what I've got. This is homogeneous first equation, and x3 plus 4x4 equals to 0. So if you remember, I asked you, I said that, okay, so let's say this is alpha, this is beta, two free variables, right? Then you can write it like that. So -3. So x2 is alpha 1 and zeros everywhere else. And here is -2. Then x2 0 because it's free variable. X3 is -4 and 1. So what is what is important, that you see, if you have 1 here, so because your free variable x2, right? So then here you will have 0, and vice versa. Here you have 0 because another free variable x4 cannot depend, it's free, right? It cannot depend on x2. So, but here you have 1. So the result, you know that these corresponding columns here, these vectors, they always will be linearly independent. It means that these vectors form a basis for the space of solution of the homogeneous system, right? Because why? Because first of all, they form a spanning set, right? And second, because any solution can be expressed through linear combination of these vectors. But second, they are linearly independent, which means they form a basis. Is it clear or not? Any questions here? Because you will be asked to find a basis for the space of solutions of the homogeneous system.
I have a question about what you wrote below for the proof.
Okay.
It says, bring the system of linear equations to reduced echelon form, and then number of free variables n minus r. Is that number of free variables equals n minus r? Or?
Yes.
Okay.
Because what is the total number of variables, of unknowns? Is n, right? Because it's n, because you see, we started with n unknowns, right?
Right.
So, but then you know that what will be the number of free variables? is the number of unknowns minus the number of leading ones, right?
Right, okay.
But number of leading ones is exactly equal to the rank, right? As we know.
Right.
So
Okay.
that's it. So essentially, from here you can see that this statement and this statement. So these two statements are equivalent, right? Essentially, because from one immediately follows another. Is it clear or not? Any questions? Yes, please. Are there any questions? Okay. So let me formulate another corollary. So,
Professor, can I ask can I actually ask a question before we start this next topic?
okay. Go
When
ahead.
I was doing the homework, I seemed a little bit confused on the difference between span and basis. And I know we kind of covered it, but in an example, if it asks us like to find the basis or find the dimension or find the span, how would that just be written out? Because I feel like I keep getting them confused, or I just have a bunch of stuff that I can write out, but I don't know.
Sure. So, okay, for example, here, let us consider the column space of this matrix. So, by definition, column space of a matrix is the space of all possible linear combination of columns, right? Is it clear or not?
Yes,
So,
that's clear.
it means that I can say that the column space is spanned by all columns of this matrix, right?
Okay, so the span would hold the vectors that create combinations of different.
Yeah, so essentially, if you have that your vector space is a span of v1, v2, vn, right? So it means that any v belonging to the vector space can be represented as some linear combination of vectors from the span. Right?
Okay, so then if it asks us to have a basis from the span that we're given.
So you see, but span doesn't mean that all these vectors here are linearly independent, right?
Okay.
So which means that they can be linearly dependent. But the basis, it's the spanning set which contains only linearly independent vectors, right? By definition of the basis. So in other words, it's the minimal spanning set. So how to get basis from the spanning set? You just look at the spanning set and determine which vectors are linearly dependent. So if you can express, for example, if you have that v2 is equal to say 3v1, right? Then you know that you can just throw away this vector without changing the spanning set, the span, sorry. So essentially, you can eliminate this vector from the spanning set, and span stays the same. So all possible linear combinations will stay the same. Why? Because, for example, in this case, you can just replace these with 3v1, right? So no problem. Still, just span stays. I can still express any vector from the vector space through the linear combination of vectors from the span, right? I don't need vector v2 because I can replace it by 3v1, and that's it. So this is the difference. So we have proven that span can be can have whatever number of vectors essentially. So for example, I can always add here 4vn, right? And just increase the number of vectors in the span. Will it change the span? No, I know that because this vector is linearly dependent with respect to this, right? Is it clear or not?
Yes, that's making it a
So,
little bit.
yeah, I can increase the span using linear combination of vectors, right? Any linear combination of vectors. I just increase the spanning set, but the span will stay the same. So which means all possible linear combinations will be the same as we have shown, because we have shown that if one vector can be expressed through the linear combination of others, you can, without losing anything, just throw away from the spanning set this vector because it doesn't bring any new information. So from the other point of view, all bases, we have proven that they have the same number of vectors, which we call dimension of the vector space. So essentially, idea is the following: that span can have whatever number of vectors which is more or equal to the number of vectors in the basis, right? But the basis always has specific number of vectors corresponding to the dimension of the vector space.
So a span doesn't imply a linear independence between the vectors.
Between the vectors and the spanning set, right? But the basis, by definition, requires vectors to be linearly independent.
Thanks.
Okay.
So a spanning set could have the zero vector, but a basis could not.
Yes. But I mean, it doesn't have a sense to have a zero vector in the spanning set because it doesn't add anything, right? Essentially. You can get the zero vector from any other vector from the spanning set by multiplying it by zero scalar, right? So it doesn't change anything. But of course, in the basis, you cannot have a zero vector because zero vector, as I said, it's linearly dependent with any other vector from the basis. Clear or not? This is very important. It's good that you're asking these questions because this is extremely important topic.
So the basis is the most simplified version of the span.
No, the basis is the most simplified version of the spanning set.
Okay.
Because span, like here, it means all possible linear combinations of the vectors in the spanning set. Okay?
Okay.
Okay, now let me just formulate the corollary. The proof is simple, and I will leave it for you. Just you can read it, so it's just a few lines. It's in the book. So where the matrix A is n by n, these statements first, the rank of A is n. Second, A is non-singular. Third, the rows of A form a linearly independent set. the columns of A form a linearly independent set. And 5, any linear system whose matrix of coefficients is A has one and only one solution. So these statements are equivalent. So first of all, if the rank of A is n, then we know that in reduced row echelon form, so if the rank of n by n matrix is n, so we will have n leading ones, right? So it means that in the reduced row echelon form, it will be nothing else but identity matrix, right? So just with ones on the diagonal. A is non-singular. Obviously, if you have if you have no free variables, right? If you have n leading ones, so A is non-singular. So then we know that rows and columns of A, so the number of linearly independent rows and columns of A is equal to number of leading ones, which is equal to n, right? Already, and the columns of rows, columns. And then any linear system whose matrix of coefficient A has one and only one solution. But this is exactly a definition, essentially. It's all we have proven the theorem that if A is non-singular, right, then there will be one solution. Or you can say that, okay, I will just take this linear system and bring it to the reduced row echelon form. And then I will have just x1 equals to the right-hand side, x2 equals to the right-hand side, and so on. So you will have, definitely will have a solution, and there will be only one solution. So that's it. So if you like, you can go through the details in the book.